Hello students, and welcome to today's lecture where we are going to continue to go over batteries. And in particular, what we are going to do is we're going to go ahead and mess with one form of the battery, which is the cell voltage, or the voltage of the cell, okay? And so this is essentially us figuring out the total chance of this happening, or the chance that a electrochemical reaction or that a battery will work. So what we're actually working with here is that we're going to be still working with this reaction right here, okay? This equation, essentially, all right? And we're kind of conceptually messing with this equation here. And remember that this is the Gibbs free energy equation, where delta G ends up being how much work we could do, okay? So that's how much power we can get out of the battery. And it equals essentially N, which is the number of moles, okay? Which, you know, that one's conceptually easy for us. The bigger the battery, the more work we can get it to do, times a constant that we're not even going to worry about, times E, which is the cell potential, okay? And this is what makes up the battery, okay? So we have how much of the stuff there is and what makes up. And today we're going to figure out how we calculate the math for that right here, okay? One other thing that I need you guys to know is that in general, for a reaction to happen, what'll happen is that we need to have a positive E, and that'll give us a negative delta G. So in order for work to happen, our change in Gibbs free energy has to end up being negative, okay? And that should make sense here because we have this negative sign in front, okay? So we have to have a cell voltage that's positive and a negative delta G. If it goes the other way, that's an electrolytic battery, and that's usually what happens when we end up forcing it to go in an opposite directions. So for instance, when we charge it, we're changing the direction that the flow is going, okay? And if we end up having no voltage at all, then we end up having a dead battery because, you know, there's nothing flowing, all right? Okay? So essentially what cell potential is this is our potential for kind of movement, and the higher it is up our line, the more likely that we're going to have movement, okay? And it's cell potential, and it's, you want to kind of think about it as like cell potential energy that's going on here, okay? So for us to go ahead and find our standard potential, what we are going to be doing is we're going to be using a chart, and we're going to combine what are known as the reduction potentials in a cell, all right? And so the cell is going to be a combination of the reduction potential at the positive terminal minus the reduction potential at the negative terminal, okay? So let's go ahead and take a look at what that is, okay? Often what'll happen is that we're going to have a list, and this is what's known as the standard reduction potential list, okay? And it shows what happens when different compounds are reduced, which means that they gain electrons, all right? And it's and this number right here is the voltage. It kind of says how likely that is to happen, okay? So for fluorine, it's like super, super likely, okay? For lithium, it's super, super unlikely that it's going to gain electrons, okay? Now, what we're actually doing in this thing, okay, is what we are actually making a cell, and what we're doing is we're actually adding the information, we're adding the reduced side, how likely that is, and we're adding that to the oxidized side, okay? So that's what we're actually doing here. But I want you to notice that when we write this, do we have any oxidized reactions? Okay. So an oxidized reaction is going to be one where we have lead and it loses electrons. Okay. And we don't have a single one here. Okay. So what we do as chemists, and especially as lazy chemists, is we're going to go ahead and say, okay, we don't have any oxidized reactions on our table. However, I know that the potential for this to be oxidized is the exact opposite potential of it to be reduced. Therefore, what we end up doing is we end up changing the reduction potential equation just a little bit so that it's going to be essentially whatever the reduction potential of the cathode is minus the reduction potential of the anode. Okay. And the reason that we do it this way is because that way we could just use the straight numbers that are on here. Okay. So we're going to go ahead and use an example here, and we're going to use a copper zinc battery. Okay. So a copper zinc battery, what normally happens is that the electrons from the zinc go to the copper. Okay. So in our battery, we would normally have copper, and that's going to be minus whatever the reduction potential for zinc is. Okay, and this is for our lazy way. Okay, so this one's going to be our lazy way. And for our E cell, for this one, we're going to go ahead and do it the official way. Okay, which is going to be our reduced plus the chances that it's going to be oxidized. Okay. So our cell, we're going to go ahead and put X here for this one. And the chances that carbon is going to be reduced, we're going to go ahead and look at our table here. Okay. Sorry, not carbon, but copper. So copper is Cu2 plus 2 electrons makes copper solid. Okay. So the chances that this is going to be reduced is 0.34. Okay. Okay. To that, we're going to go ahead and add the chances that this is going to be oxidized. So we're going to look at zinc. And zinc, we don't have zinc's oxidation numbers. Okay. But we know that this is going the opposite direction, okay? And the chances that it's going to go in the opposite direction are going to flip this sign because it's going the opposite way, okay? So it's going the opposite way, that means that it's in reverse, okay? So instead of 0.76, we're going to put in, instead of negative 0.76, we're going to put in positive 0.76, okay? And that total is going to go ahead and give us our the potential for that cell. Okay. Now we'll go ahead and do it the lazy way. Okay. The lazy way is saying, nah, I'm just going to flip my sign. Okay. Now the reduction potential for copper, well, that's still 0.34. Okay. That doesn't change. Okay. Then we're going to go ahead and look at our anode, and we're going to look at the reduction potential for our anode. Okay. And we're going to look for zinc, and it's negative 0.76. Okay. And look, here we're subtracting out a negative 0.76. So that makes it pretty darn easy. Both of these end up equaling 1.10, okay? All right, And that's how we end up solving the voltage of the cell, okay? And one thing that I want you to take note of, especially in this graph right here, is that the bigger the gap, the more the voltage of the cell is going to be, okay? So that means that we could go ahead and take a look and say like, oh, well shoot, if we have lithium, okay, and it's going to fluorine, that's going to give us the biggest gap. That means that, you know, on this table, the best possible materials that we can use for this battery that we want to make is going to be lithium, okay, and that would be on our anode side, and fluorine, and that would be on our cathode side. Now, obviously, fluorine gas, it's a little suspicious. You don't want to be working with that. But that's how we can maximize the amount of energy that we use in a battery, okay? This should also explain why, when we're messing with batteries, and when we think of batteries, we think of lithium-ion batteries. Because look at that. Look at how far down this table lithium is, okay? So lithium is going to make a great battery because of that. Because it's so willing to lose its electron to something else, okay? So this is how we mess and kind of work through these kind of cell potentials right here, okay? And remember that this number right here, G, the higher E is and the higher N is, the greater amount of work that we can do, okay? So that's really one of the big key things that I want you to be able to manipulate and explain. Like when we're working with our battery, explain how we can make it so that it can do more work, because that's what's actually useful for us, okay? Now, let's go ahead and take a look at this one here now. Okay, here, this is our galvanic cell here. We have the electrons leaving the cadmium and going to the Ag. Therefore, if we're going to go ahead and look at this one here, we're going to look for the reduction potential of the cadmium going to the silver, okay? Since the electrons are leaving the cadmium, this one's our anode. And since they're coming to the Ag, the silver, this is going to be our cathode, okay? Now, we would go ahead and take a look over here, and we'd say, okay, our cathode, okay, is 0.80, all right? Oh, let's make this a little bit bigger. Okay, we'll put in an X there. Our cathode is going to be 0.80, okay? We'll subtract from there our anode, and we're going to have to look back here. Let's take a look here. Our anode is cadmium, so let's go ahead and take a look here. Cadmium, let's find it. Cadmium is negative 0.40. So we'll subtract negative 0.40, okay? And then X is going to equal 1.20, okay? So this is a pretty good battery, okay? This is giving us 1.2 volts, okay? And so this is what we're going to be looking for in this particular section right here, where we're going to be looking for the delta, the cell of the reaction. Okay, and we don't need to worry about that. All right, so that's going to go ahead and close us out for figuring out the voltage of these electrochemical reactions. From here, you should be able to do the worksheet that's going to be associated with this section. It's a pretty simple one, though. So I'm going to go ahead and leave off. And remember, stay lazy.